This is Tammy, and I am your kitchen table math tutor. On this channel, we'll talk about algebra, graphing. I'll share some study tips that will save you time and stress, and also lots of encouragement, because math can be challenging, but you can do it. In this video, we'll be talking about systems of equations in two variables, the graphing method. Also in this series, solving systems of equations by substitution, systems of equations by the addition-elimination method, and using systems of equations to solve applications. Okay, so before I actually move into doing the solving, I'm going to talk a little bit about some possibilities and some vocabulary, because I think it's always useful to know what kind of outcomes we can have. And also, a lot of courses that I've seen use the vocabulary consistent and inconsistent, and dependent and independent in talking about systems of equations. So I want to make sure that that is clear and established before we go on to actually using some of that terminology. So there's really only three things that can happen when we have a system of linear equations in two variables. We can have lines that cross in exactly one place, like the first graphic shows. We can have two straight lines that never meet, so we have parallel lines, as the second graphic shows. Or we could have two lines that lay right on top of each other. And that's really hard to show in a graphic. So the third graphic looks like there's just one line. Really, that's supposed to represent two lines laying right on top of each other. So going on to talk about that vocabulary I sort of touched on earlier, the vocabulary talks about two different things. It talks about solutions and it talks about lines. So the solutions, if we have a system that has at least one answer, it could have one answer or it could have infinitely many answers, that system is referred to as consistent. The one that's different, the one that stands out, the one that you may be asked to use in an answer at some point, inconsistent. So those parallel lines are inconsistent because they have no solution. The other thing that we can talk about in reference to systems of equations are the lines themselves. So if I see two lines, those systems are referred to as independent. So we have one independent system where we see two lines that cross in one place. We have another kind of independent system where we see two lines, but they are parallel. So just because something is inconsistent does not also mean that it's sort of special in another way. When we move on to the system that is dependent, that is the consistent system where we have two lines laying right on top of each other. It has infinitely many solutions, so it's consistent, but when we look at it, we only see one line, so it is dependent. Usually the way I memorized these for myself was I looked at the ones that were different. So that's why I have them highlighted and why they sort of appeared in a different way on the screen, because if you can think of the things that are the differences. So the inconsistent system with the two parallel lines, and the dependent system with the lines that lay right on top of each other, I think that is a more efficient way to do it than to just try and memorize this graphic or some other presentation that your instructor has given you. Because if you know which ones are inconsistent and which one was dependent, the rest can just fill in. Okay, so moving on. Solving systems by graphing. And this is going to be just a list of things to do. We're actually going to practice those things to do in just a moment. But we can solve systems of equations by graphing by hand. Now, there's nothing wrong with solving it by hand. There's certainly nothing bad about it. Mostly, when we talk about solving systems by graphing, we are talking about a calculator method. But a lot of times instructors will have you prove that you can do it by graphing. So there may be a test question where it just says graph the two systems on the same coordinate plane and solve. So to do that, both equations must be set equal to y. So essentially, we're going to treat this kind of like graphing any other line that you would be given. Graph each line on the same coordinate plane. Look for the intersection point of the two lines, if there is one, and then report your answer as an ordered pair. If the lines do not cross, there are different ways to report that. So if they are parallel lines, a lot of times you will use the word inconsistent, or you would describe them as parallel lines. If they are the two lines that lay on top of each other, you would say that the system is dependent, or you would report it as in set builder notation. We will talk more about that in future videos. Solving by graphing, usually if you have to do it by hand, you'll be given one that does actually have a solution. So on the calculator, which is the more common method, both equations must be set equal to y. So that's the same first step as solving it by hand. You enter the two equations into the y equal screen of your calculator. You find the intersection by using the intersect feature, and you report your answer as an ordered pair, just like you would if you were solving it by hand. Now, if those steps are unfamiliar, if you've maybe seen it once in class but you don't quite remember, I will be demonstrating how to do that on a TI-8384 type calculator. Okay, here's our first example of solving a system of equations by graphing. I have my two equations here, negative 4x plus y is equal to 5, and 2x minus 3y is equal to 15, and my directions. The directions are not something that would necessarily appear on a test, so you would have to know to solve for both equations for y, to graph each line, and then record each answer as an ordered pair. I find it useful when you're practicing to have the directions in front of you. Okay, so the first thing I have to do is I have to solve both equations for y. So I'm going to solve this first one for y. I'm going to solve it in pink. So I have negative 4x plus y is equal to 5. So my goal is to solve for y. Right now, y is not alone. I've got a negative 4x here. So I'm going to treat this just like an equation. If I wanted to move that term to the other side, I would add 4 to both sides. In this case, I'm going to add 4x. So I get y is equal to 4x plus 5. So the reason I can't just put those together and say that I have 9x is because they are not like terms. They can sit next to each other, but that's all. So also, if you said 5 plus 4x, that's perfectly fine. I tend to write it in this form because this is the y equals mx plus b form. And that reminds me, okay, which is my y-intercept and which is my slope? If you're really good at identifying that, and there are some people who are, that's fine. You can put it in either order. So now before I go on to graph this, I'm going to solve the other equation for y as well, just so that that's all done, and then we can just do the graphing part. So I have 2x minus 3y is equal to 15. Well, I'm going to kind of think of it the same way. I've got to get that y by itself, and it's not. It's been multiplied by a -3, and then they've added 2x to it. I'm going to undo what they did, and I'm going to start by subtracting 2x. And I'll do that to both sides. So I have -3y is equal to -2x plus 15. All right, well, this is getting closer. So my y is almost alone. It's been multiplied by a -3 though. So if I want my y by itself, I divide by a -3. If I do that to one term, I have to do that to all the terms. And I get y is equal to -2 divided by a -3 is a positive 2/3. Now I know the numbers, nothing happens to the numbers, and sometimes that seems a little strange to change the signs like that. But we are dividing a negative by a negative. Even if the numbers don't change at all, and this fraction cannot reduce, so they won't change, I still have to say that it's positive. And then 15 minus 3, or 15 divided by a -3 is -5. So I'm going to switch back to my pink color, and I'm just going to define what the y-intercept is and what the slope is before I start graphing this line. So the y-intercept is 0, 5. So I know that first part is 0 because the x value of any y-intercept is 0. 5 is the plus b, or the beginning part of that line. My slope, and I will just say m, is the number with the x. So here we have a 4. The thing is, slope always has two pieces. So I have to say 4/1. What that slope tells me, the top number is our y values. So that would be up or down. It's positive, so we're going up. That bottom number is connected to the x's, so that is left or right. It is also positive, so that is to the right. The thing about slope, though, is that you can also reverse those directions, and you will draw the same line. So let me show you what that looks like. So right now we have a y-intercept of 5. So I'm going to plot that point because that's the only point that I know for sure is on my line. I'm going to go up 4 units and 1 unit right. And that's the next point. Now, the trouble with this is a lot of times when you are graphing by hand on a test, your instructor will say, define 3 or more points. And it looks like I've just run out of graph. So I'm going to use that idea that I can just reverse direction. So instead of going up 4 units, I'm going to come down 4 units. Instead of going 1 unit to the right, I'm going to go 1 unit to the left. And I will be drawing the same line. So if I go down 4 units and 1 unit left, there's my next point, and it's directly in line with the other two. Now, I'm going to continue to draw more points just because I don't know where that intersection point actually is, and I want to be able to see it very clearly. So I'm going to continue to follow my pattern, the 4 units down and 1 unit left, 4 units down, 1 unit left. Now, this is something that I tend to do anyway. I tend to, if I'm graphing a line, I'm going to put as many points as I can, because then if I use my ruler or whatever I do and the line comes out a little bit wonky, my instructor still knows where all those points are, and that I don't think my line is sort of curved off to the left or to the right or something. So on a screen, this is a little more difficult. I will draw a line to connect those points. Okay, and so I drew my line off the edge of the grid, and I'm going to put arrows on it just to show that it goes on for infinity. And now my pink line is done. So now I'm going to move on to the green line. The y is equal to 2/3 x minus 5. So my y-intercept is the b value, or the beginning. So that is 0, -5. My slope this time is a fraction already, so I don't have to deal with any of that, putting it over 1 or any of that stuff. I have 2/3. My 2 tells me is positive, so I'm going to go up 2 units. The 3 is 3 units right. I can also reverse those directions if I need to. I can go down 2 units and 3 units left. So I'm going to start off with just the first set of directions, the 2 units up and 3 units right. So first I'm going to find my y-intercept of 0, -5. And I'm going to go up 2 units, 3 units left, or right, pardon me. 2 units up, 3 units right. And that, now I could continue with that. And if I were just drawing this for myself, I probably would, just because I'm a little bit, I like to be certain of where my points are. But I could also say, well, that's taking me further and further away from that pink line. So obviously, I'm not going in the right direction, and there's never going to be an intersection point that way. If I want to go closer to my pink line, I'm going to go down 2 units and 3 units right. Or 3 units left. Pardon me, goodness. Down 2 units, 3 units left. So now I'm going to draw my green line. Okay, so there's my green line, and I'm going to put arrows on the end. I've drawn it across the edge of the graph. And even before I drew this green line, you could probably see where they intersected. And that's kind of why I did it this way, because this point right here is the intersection point. So we have to name that point, and that is going to be our answer. So we've done solving both equations for y. We've graphed each line, and now we're going to record our answer as an ordered pair. So if I name that, that's -3 and -7. And that is the solution to that system. Okay, I wanted to do one more example of solving a system of equations by graphing and doing it by hand. So we're going to go through this one, and there is something a little special about this one. I'll just put that out there right now. That's the only reason that I'm showing it, instead of just moving on to solving systems of equations on the calculator. So I've got my two equations. 2y minus x is equal to 6, and 2x plus 18 is equal to 14. And I have my instructions here too. So solve both equations for y, graph each line, and record each answer as an ordered pair. So I'm going to do basically the same thing that I did the last time. I'm going to solve each equation for y, and then we're going to graph both equations on the same graph. So this time my pink equation is 2y minus x is equal to 6. So even though this is in a different order than the one before, I still got to get y by itself. It doesn't really matter where the y is, I just want it isolated. So to do that, the first thing I'm going to do is I'm going to add x to both sides. If you want to say 1x, you absolutely can. Some people really like to see the 1 in front of the variable. Other people, it doesn't matter, or they would rather not see it. So I have 2y is equal to x plus 6. Okay, so I'm still looking to get that y by itself, and we're pretty close, but it's still being, that y is still being multiplied by 2. So I'm going to divide everything by 2. So I get y is equal to, and I can say x over 2, or I could say 1/2 x. I think when I write this out, I would prefer to see the 1/2 x, just because it looks more familiar. And then 1/2 x plus 3. Okay, well that one wasn't really very different, except for the x over 2 and knowing that that's 1/2 x. Let's try the next one. And the next one is 2x plus 18 is equal to 14. Oh, okay, this is odd because my directions say solve both equations for y, but this one doesn't have a y in it. So if I have an equation that has only an x variable, I'm going to solve for the x variable because really that's the only thing that I can do. So I'm going to highlight my x and say, all right, well, I'm just going to do the same thing as the y. This is just like solving any other equation for x. So I'm going to subtract 18 from both sides, and I will get 2x is equal to -4, and then I'm going to divide by 2. So I get x is equal to -2. Okay, so this solve is probably more familiar because it's just like solving any other equation for x. The thing that might be a little unfamiliar is what does that mean in regard to graphing? So I'm going to graph the pink line first because the pink line is probably the one that we're most familiar with. So we need a y-intercept. And like before, I'm going to write that as an ordered pair of 0, 3. And we need a slope. And the slope is 1/2. Right now it's positive 1/2, so I'm going to go up 1 unit and 2 units right. I could also reverse that if I wanted to. So I'm going to graph the pink line, and then we're going to go on to that more unusual green line. Okay, so I'm going to start up here at 0, 3. That's the only point that I know is there right now. And I'm going to follow my slope. Up 1, 2 right. Up 1, 2 right. Up 1, 2 right. Up 1, 2 right. And up 1, 2 right. Now that's got part of my graph covered, but I think because I'm not real sure where those lines are going to meet, so I'm going to go back the other way as well. I'm going to come down 1 and go 2 left. Down 1, 2 left. Down 1, 2 left. Down 1, 2 left. Down 1, 2 left. So that draws my line across the entire graph. So I will go ahead and actually sketch that line. Okay, there's my pink line, and I'm going to put arrows on the end just to show that it goes to infinity in both directions. So now I'm going to deal with this green line, this x equals -2. And really what that means is that every single x value on that line is -2. So I could, if I wanted to, do a little t-chart where I can say, okay, x is -2 all the way down. And I could choose as many values as I want. I don't need to choose just 3. I could do 6 or 8 or however many you want to do. But my y value, no matter how many -2's I have, my y value could be anything. My y value could be a -4. It could be 0. It could be +6. Really, any y value that you want to choose, including fractional values. Now, if you're graphing by hand, I would not recommend choosing fractional values, but you could. Those do exist. So now I'm going to graph this thing, and I'll use the values from my t-chart. So I have -2, -4, right down here, -2, 0, right here, and then -2, 6, right up here. And I will draw that line. Okay, there's my green line, and it's maybe a little bit off, but it's close enough. And again, I'm going to find my intersection point the same way that I did before. I'm just going to see where those two lines cross, and I'm going to report that as an ordered pair. So in this case, it is -2, +2. Okay, so the thing that makes that so different, and the thing that makes it so important to be able to graph that by hand, is because graphing calculators, at least the TI graphing calculators, will not draw a vertical line because it is not a function. So if you look at your calculator, you have that y equals button, and if you look at that window, everything says y equals. There is no place for x equals. So if you are presented with an example like this, you would have to graph it by hand. But it's really not so bad, because once you establish that what your x value is, everything on that vertical line is the same x value. So it's really just a vertical line at x equals -2. And x will equal -2 every single place on that line. Okay, so we are going to look at just a couple more examples, and these examples are more special cases. And certainly you can just follow the same procedure that we did before. And I still have those rules on the screen. We're going to solve both equations for y, graph each line, record each answer as an ordered pair. So you can follow those directions and you will get to a correct answer, whether it's a special case or not. The thing that I want to point out here is sometimes it can save you some time and some trouble if you kind of analyze what you're looking at first. And if you can kind of decide what you think is going to happen to that system before you ever graph out the lines on paper or on your calculator or however you're doing it. So looking at these two systems, I am not going to graph them, but we are going to solve them for y. So this first one, I have negative 2x plus y is equal to negative 6, and negative 2x plus y is equal to 4. Now, already, you can look at that and say, well, it's the left-hand side of that is the same on both of them. So something is going to have something funny's going on there. And you'd be right. So let's try and solve them out, and we'll see what is actually happening. So we've got negative 2x plus y is equal to negative 6. And I will just follow the same procedure that I did before. I want y by itself. It's not by itself, so I'm going to add 2x to both sides. On the left-hand side, it cancels, and I'm left with just y is equal to 2x minus 6. Moving on to the second equation, I have negative 2x plus y is equal to 4. I want to get y by itself, so I'm going to add 2x to both sides. And I get y is equal to 2x plus 4. Okay, so now I've got them both solved for y. And I step back and I kind of look at what do I have. Well, the slope of both is 2 because I've got 2x minus 6 and I've got 2x plus 4. So immediately I know that this is a special case for sure because my slopes match. My y-intercepts do not match. So if I have two lines that have the same slope, they are parallel lines. So going back to that idea, I have the same slope. So I have parallel lines. And if I put that in my calculator or if I draw that on my paper, I know exactly what that picture is going to look like. If I need to use some specific vocabulary to describe that, I could say that these lines are inconsistent because there is no solution. I could also say that they are independent because we do see two lines. Okay. So if you want to practice that by graphing it out on a sheet of paper or putting it into your calculator, please feel free to do so. I am going to move on to the next system. So if you would like to pause the video, please feel free to do so. Okay, so my next system says I have negative 2x plus y is equal to negative 6, and negative 6x plus 3y is equal to 18. So the first one is exactly the same as the first equation in the previous system. So we know how that solves out. We know that that solves out to be y is equal to 2x minus 6. If you want to go through the solve again, you certainly can do that. And now my second equation. Well, that one's looks kind of new. I haven't done that one before. So I will actually work through that one. So I have negative 6x plus 3y is equal to negative 18. Okay, well, the goal remains the same. I got to get the y by itself. So I'm going to start by adding 6x to both sides. So I get 3y is equal to 6x minus 18. All right, well, that doesn't really look like anything like the other one right now, but my y is not alone yet. I've got to continue to solve for y, so I'm going to divide by 3. If I do that to one thing, I do it to everything. So I have y is equal to 2x minus 6. Oh, wait a minute. That is exactly the same. So not only is my slope the same, the 2's in front of the x, but my y-intercept is exactly the same as well. Okay, so this has to be exactly the same line, which means that these two lines are going to lay right on top of each other. So if I define that in words, I have the same slope, same y-intercept, I have the same line. If I were to use some of that vocabulary we talked about in the beginning, these lines would be consistent because they have infinitely many solutions, and they would be dependent. Because when I looked at the picture, I would see only one line. And if you have a graphing calculator in color, this shows up really well because it will draw the one line in like a red color and maybe the other line in a blue color, and you can see them laying right on top of each other when you actually draw it. Even a calculator that does not offer color, you can still change the thickness of the line and you can still see it the same way. All right, so on to solving on the graphing calculator. And this is probably the way that you are going to solve systems of equations by graphing most often. Um, on paper, it's more of a prove that you can do it kind of thing. If you're actually using this to solve a system in an application problem, or just because you're looking at a system and your instructor is just saying pick whatever method you want and it looks like graphing would be easiest, you're probably going to do this on your graphing calculator. So the rules for that are solve both equations for y, so that's not different than solving by hand. Put both equations into the y equals screen, and you would do that as y equal as y1 and y2. Then you would graph. You would use the intersect feature to find the solution, and you would record your answer as an ordered pair. Now that seems like more steps than graphing by hand. And I guess it is, but really what you're doing is just typing the equations into your calculator. So I am going to switch over to my calculator emulator now, and I will show this procedure. A lot of times you see it in class, and some people know how to do it really well, and that's awesome. Sometimes if you don't quite know how to do it or can't remember the steps or have only seen it once in class, um, sometimes seeing it again can be really valuable. When we see something for the first time, when we're trying to process the math and everything else that we're also seeing for the first time, sometimes the calculator kind of goes by the wayside. And it is such a powerful tool that I like for everybody to be able to see it in use and try it themselves and have that time to play around with it. Okay, so I am using the Chematech calculator emulator. It is a TI-84 Plus Silver Edition. So the screen does not have color, but that's okay. It has all the same functions as some of the other newer calculators. It is free to use for anyone. I will put the link in the description box. So if you are at home, if you've forgotten your graphing calculator, if you don't have one yet, this is a great one to use and practice. Okay, so the first thing that I want to do is I want to enter those two equations into my y equals screen. So the y equals button is at the upper left-hand corner. So I'm going to hit y equals. And you can see that I've already entered these two equations into my y equals screen. They were both set equal to y to start with. So I have parentheses 1/2 and close my parentheses x plus 3. And then for my y2, I have parentheses 3 divided by 2, close my parentheses, x minus 2. So none of that is surprising or strange to type in. If you're wondering what X I used, it is the button right next to the alpha key, and that has an X, a T, a theta, and an N on it. So it actually has 4 symbols. When you use it, you're just going to, when you just push the button, you'll get an X. And that's probably the easiest one to get to. Okay, so now I've got that into my Y screen. Now I'm going to hit graph, and graph is at the other end of the row of buttons from the Y equals. It's at the top right-hand corner of your calculator. And there's the first line. There's the second line. And now the calculator is done drawing. So, and that's great. You know, I can kind of look at it and I can see that these lines intersect in quadrant 1. And maybe I could make some guesses. I mean, it looks like maybe 5 or 6 or somewhere in there for an X value and maybe the same for a Y value, but I don't have to guess. The great thing about the calculator is that it will tell me exactly where those two lines intersect. So if I go to second, which is either blue or yellow, it's right under the Y equals button and right over the alpha key. And the calculator puts a little up arrow in the corner. And now I want to go to trace. Trace is just to the left of graph. So the title of the menu is calculate, and that's what's in blue over the trace button. So now I want to go to option 5, which is intersect. I can use my down arrow to get there. I can also just type 5 and the calculator will select that option. Okay, now it's going to ask me, we've gotten back to my graph screen. It's going to ask me 3 questions. So the first question is first curve. And yep, that's the first curve. So I'm going to hit enter. Second curve, I'm going to hit enter. And now it wants me to guess. I could move that cursor, the little blinking cursor, closer to that intersection point. There's only one intersection point. So I'm just going to hit enter again and make the calculator find it. Okay, so now the calculator says that my intersection point is 5, 5.5. So when I write my ordered pair, it would be my x value of 5, my y value of 5.5. The drawback to this is if my intersection point is off the screen, I would have to make my window larger and try and find it so that I could use the intersect feature. The other, and that's sort of a pitfall as well if I'm going to actually see both lines, because I could have a system where I can clearly see one of the lines but not the other one. Maybe in my standard viewing window I don't see either one of them. So graphing, solving a system by graphing is always a little bit fiddly no matter which way you do it. The calculator is usually the better option though, because if I were to graph this out on paper, yeah, I'm going to use a ruler. I'm going to be careful. I'm going to draw as many points as I can, but I still might miss that 5.5. If one of my lines is just a little bit off, I could think it's 5.5. I could think my answer is 5.6. It might look to me like 5.75. So it really, graphing is maybe not the best way to solve a system, but it is certainly an option. Some people love to graph, a lot of people don't. I can't tell you what is going to be the best for you. I can only tell you, how to do it and what the pitfalls may be that you encounter. This is Tammy, your kitchen table math tutor, saying thank you for watching. If you found this video helpful, remember to like, subscribe, and share with someone else who might find it helpful too.